Hello everyone, and thanks for watching Edupedia World videos. In this video we'll begin a new unit called Optics, and the topic we'll start with is light waves. Now the nature of light has puzzled physicists for a very long time, and the debate has been about whether light is made up of waves or particles. We studied both of these things. Particles we studied pretty much mainly in kinematics when we dealt with point objects, but even a dust particle or an atom or molecule can be treated like a particle. And then we studied extended objects when we moved on to rigid body dynamics. We studied waves of two types, longitudinal and transverse waves. Longitudinal waves would be sound waves, transverse waves would be waves on a string, and in fact light waves, which is what we'll study in this video. So historically, the first proof that light was made up of particles was given by Newton. And he made up a theory which proved the laws of reflection and refraction, assuming that light was made up of particles. At the same time, there was another physicist, Huygens, who put forward a theory that light was actually made up of waves, and he created his own theory on the basis of which he was also able to prove the laws of reflection and refraction. So we had two theories, both of them explained the experiments, so it was a matter of interpretation, and the scientific community had more faith in Newton's writings because he had a lot of respect from his other work on gravitation and calculus. Then much later than that, there was a scientist, Young, who did a famous experiment called Young's double slit experiment. We'll study this experiment in very detail when we study light waves. And then the problem with this experiment was, this experiment could not be explained on the basis of particle theory of light. This experiment showed a phenomenon of light which we studied before, which is called interference. And interference is only showed by waves, it is not showed by particles. We saw constructive and destructive interference when we were talking about waves on a string and sound waves. So Young's double slit experiment was an experiment that could only be explained on the basis of waves theory of light. So then for a long time the scientific community assumed that light was made up of waves until another phenomena came about, which is called the photoelectric effect. Now Young's double slit experiment we'll study in this video because it's light waves. Then we'll move on to light as particles, and when we later move on to modern physics, that's when we'll be studying the photoelectric effect. But right now all you need to know is that the photoelectric effect could only be explained on the basis of particle theory of light. It could not be explained on the basis of waves. So then the real debate started, because we had some experiments and some phenomena like interference because of the double slit experiment, which could only be explained by assuming that light was made up of waves, but we had other phenomena like the photoelectric effect which could only be explained by assuming that light was made up of particles. So then an understanding was reached, and right now we believe that light has what we call dual character, which means that it behaves both like particles and waves. That might seem a little flimsy, but the real victory came when we learned that in fact all particles have dual characters in electrons, protons and everything else, and that fundamentally changed our understanding of particles and waves, which gave rise to quantum mechanics, which we'll not be studying in this course. So for this course what we'll be doing is, right now we'll study light waves and the various phenomena that prove that light is made up of waves and that light waves gives up. And then we'll be studying light as particles, which will give rise to geometrical optics. And later when we move on to modern physics, we'll study the photoelectric effect. So the study of light waves begins with Huygens, who was the first person to put forth the theory that light was made up of waves. So he had his principle called Huygens principle, on the basis of which he was able to explain the laws of reflection and refraction. So before this, we need to know what a wavefront is. Now we studied wavefronts a little bit when we studied waves. I'll repeat it here. A wavefront is a surface on the wave where all points have the same phase. So let's say you have 5 ropes, and each of these 5 ropes you're moving up and down. And you started at the same initial condition and you're just doing it the same thing all the time, then every point here will either be at a maxima together or at a minima together, right? If you have very long ropes and you just continue moving them up and down, starting at the same point in the same phase, then all these points will reach a maxima or a minima together. So this is what we would call a wavefront. The major property of a wavefront is that the direction of a wavefront is always perpendicular to the direction of propagation, because the direction of propagation is where light or any other energy or disturbance actually moves, and perpendicular to that the disturbance will not move at all. The analogy between wavefronts and direction of propagation is sort of like the analogy between potential and equipotential lines, right? If the electric field is in this direction, if there's a point source and the electric field is in this direction radially outward, then equipotential surfaces would be these surfaces, which would be perpendicular to the electric fields. Similarly, if the direction of propagation of a wave is in this direction due to a point source, then this would be the surface of a wavefront. All these points would have the same phase at the same time. So now that we know what a wavefront is, let's talk about Huygens principle, which suggests that, I'm not going to write it down, it's too long, but it suggests that various points on an arbitrary surface, when reached by a wavefront, become secondary sources of light. So let's say light is going in this direction. Let's say these are wavefronts. By the way, whenever you have beam of lights, you will always have what is called plane wavefronts perpendicular to the direction of propagation. Whenever you have a point source, you will have spherical wavefronts, right? Just like equipotential line. So if light is moving in this direction and you have a particular arbitrary surface, the moment a wavefront touches this surface at one point or more than one point, that point becomes a secondary source. So you have a primary source which creates waves, because of which wavefronts are created. The moment a wavefront touches an arbitrary surface, the points on the surface which it is touching become secondary sources. Now points will always be point sources, right? And they will give off spherical wavefronts. And if you want to determine the position of a wavefront at a later time, you just forget the primary waves, just focus on all the secondary sources, creating what will be called secondary waves. And the superposition of these waves will give you the new wavefront. Let's see this in a simple example. If we have a point source, this would be the wavefront at a particular time, and this we know, I'll not draw it right now, a bigger sphere with a bigger radius would be a wavefront at a later point in time. So how does that come about? So let's assume at some point of time this sphere was touched by a wavefront. The wavefronts will be spherical, so all the points on this sphere will be touched by the wavefront at the same time. At that very point, this point and this point and this point and every point on this sphere will become secondary sources. That's it. This is Huygens principle. It says that whenever any surface is touched by a wavefront, the points on that surface will become secondary sources which will emit secondary waves. So the moment the wavefront reaches this point, all these points become secondary sources. Now let's say 2 seconds later, these points will have created their own secondary wavefronts, right? So the wavefronts might be something like this. I'll use solid lines to represent maximas and I'll use hollow lines to represent minimas, right? So it'll be something like this. This point will have a wavefront of something like this. This point will have a wavefront of something like this. And so on. We'll see that with every point, right? Now what we see is, in the interior points, sometimes you have maximas and sometimes you have minimas, and because there are an infinite number of points, they will end up cancelling each other. However, if you look at this envelope, a sphere of slightly higher radius, then if you have a point here, it will have created a wavelet like this. If you have a point here, it will have created a wavelet like this, and you have an infinite number of points. So we can see by construction that every point in this bigger sphere will have a maxima. There will be no minimas here. So if you take all these secondary wavelets and you superimpose them, then the resulting wavefront will be this. Because all the interior ones will cancel, you have maximas as well as minimas. However, all of these will be maximas, so will end up cancelling. If you take an envelope like this, then you see that it's touching all the minimas. So this will actually be a wavefront of minimas, right? And you see this is actually how wavefronts propagate. Maxima, minima, sorry, this is not a proper circle, maxima, minima. So this is how wavefronts propagate, and it seems natural enough for a simple case of point source that wavefronts would propagate spherically outwards, but you can see that it can also be explained on the basis of Huygens principle, which I'll repeat once more for clarity. It says that whenever points on an arbitrary surface are reached by a wavefront, they become secondary sources of light. Now after that, all you need to do is superimpose all these secondary wavelets and you'll end up with the new wavefront. Right, and so in this case we've proved that wavefronts follow spherically outwards. Now let's use this Huygens principle to prove the laws of reflection and refraction of light. So first we'll do reflection of light. So this is a big mirror that I have. Now one thing we'll start doing, which will be slightly new now, you've seen laws of reflection and refraction before in earlier classes, and you've seen an incident ray going like this, emergent ray going like this, and a normal. But now you'll need to get used to not looking at an incident ray but looking at a wavefront. So we've talked about if an incident ray is going like this, then the wavefront is perpendicular to it like this. So if an incident ray would be going like this and the emergent ray would be coming out like this, then the wavefront of the incident ray would be something like this. The wavefront of the emergent or the reflected ray would be something like this. And now that using Huygens principle and Huygens construction, we'll only talk of wavefronts, right? So let me draw proper wavefronts. Let's say the incident wavefront or the wavefront of the incident ray is this. Let's say AB. At a previous time it was this, before that it was this, before that it was this, because they were going in this direction. At some point this wavefront touched this mirror at one point A. So according to Huygens principle, the moment this wavefront touches this mirror A, this point A becomes sources of secondary waves. So it will start emitting its own wavelets. As time passes, those wavelets will start increasing in radius and so on. Right. So the moment this surface is touched by A becomes a secondary source. A little bit later, this point will be touched by this point of the wavefront. Right, that's when the wavefront will be like this. At that point, this will become a secondary source of wavelet. A little later, this point will be touched by this wavefront when this wavefront reaches here. At that point, this will become a secondary source. And at the end, B will reach this, and at that point will become a wavefront. Right, so at a later time, B reaches here. Let's call this point C. Right, so initially the wavefront was like this. I'll draw this. Later it will be like this, then it will be like this, then it will be like this. When the wavefront is like this point is touched by the wave, so it will become a secondary source. When this point reaches here, the wavefront reaches here, this point will be touched. Keep in mind that when the wavefront is going from this point to this point, nothing in this region has actually been touched by that wavefront, so they won't become secondary sources, right? So let's say it takes time t for the wavefront to go from B to C. The new position of the wavefront, by the way, would have been something like this, except it won't be because the ray got reflected. Right? The wave is not moving forward, the ray got reflected, and our job is to make the reflected ray. So let's say it takes time t for the wavefront to go from this point to this point, that is from B to go from B to C. Then this distance would be Vt, where V is the speed of light. Right? Now if it takes a time t for B to go from B to C, then the moment B was here, A became a secondary source. So A has become a secondary source for a total time t before C starts becoming a source. Right? So by the time C becomes a source, A will already have a maximum wave. A will have a maximum wave which will have a radius of Vt. Right? Initially it was AB. At that point A just started becoming a secondary source. By the time B reached C, there was already a time t that had elapsed. If this distance is Vt, in that case this wave has been going outwards at a speed V for a time t. Right? So the envelope of the biggest wave, that started at A would be this. Right? What will be the envelope of the wave that started at C? Nothing. C has become a source for literally 0 seconds because B has just reached this point. So C will not be a wave yet. C has just started becoming a source. What we'll do is, just take a second to make the figure a little bit clearer. This should be something like Vt. Right? So now we join these two. We know that this is a point on the new wavefront because it has just started becoming a secondary source. This is a point on the new wavefront because it has become a wave for a time total of t seconds. Right? Now what we need to do is prove that every point that becomes a source at a time in between 0 and t starts producing a secondary wave, and at time t that wave has an envelope at this point. So it's going to get a little bit mathematical. Let's take this point P. Right. Let's say AP is equal to X. Right. Or actually better, let's say AP by AC is equal to X. That will make it easier. So X is a fraction. If X is half, then P is midpoint between A and C. If X is 2/3, then AP is 2/3 of AC. Right. So this is X. Now we'll draw a perpendicular here. Right. I'll just label this point as Q. Now we can see that this angle, focus on triangle APQ and triangle ABC. This angle is the same in the triangle, right? This angle is 90 degree and this angle is 90 degree. So we can see these two triangles have all angles same, so they are similar triangles. That means if AP by AC is equal to X, then QP by BC is equal to X as well. So that means how much time does Q take to go to B? It takes a time xt, a fraction of the total time t. That means P will have a maximum wavelet. I'll just not touch it yet, even though I know it will touch it. Have a maximum wavelet which will be going on for a time t dash, which will be equal to t into 1 minus x. Right? Because if the total time taken is t, it takes time xt for it to start becoming a source. Then it will only become a source for a time t into 1 minus x. Right? So this radius, let's call this r for a second. PR will be Vt times 1 minus x. Now let's join these two. Let's call this D. Now you can see this is R. You can see that similarly, just like these two triangles are similar, triangle CPR and triangle CAD are similar. This triangle and this triangle. Right? And what is the ratio of CP by AC? It is 1 minus x. That means PR by AD is equal to 1 minus x. So let's look at what we've proved so far. At time t is equal to 0, this started becoming a wave. At time t, B reached C and C just became a wave at time t, so it doesn't have any radius of its wavelets. A has been a secondary source already for a time t, so this is the maximum wavelet. Then we took a random point C and we saw that if it takes a time xt for it to become a source, then it will only have been a source for a time t into 1 minus x, which means the radius of this line will be Vt into 1 minus x. Then we actually took these two triangles, proved that those two are similar, proved that this by this is indeed 1 minus x, and what we've ended up proving is that because x was an arbitrary point, every point, this point, this point, this point, this point, x could be anything between 0 and 1. Every point will have its maximum wavelet, which will be a tangent to this line. Right? So this line was the incident wavefront, and now we finally proved that this line is the reflected wavefront. Right? Now once we proved this line is the reflected wavefront, this is 90 degree, this is 90 degree, this is Vt, this is Vt, this side is common. So these two triangles are congruent. If these two triangles are congruent, then this angle is the same as this angle. And if this angle is the same as this angle, I leave the geometry to you. Then the angle between the incident ray and the normal and the reflected ray and the normal should also be the same. Right? So it was a little bit mathematical, and I apologize, we'll do a little bit more mathematics when we derive laws of refraction. But now you see how Huygens was able to prove the laws of reflection using his own principle. Let's see laws of refraction now. So this is, let's say, medium 1, medium 2. So the light would have to go like this and come like this. Right? So instead of that, we'll make a wavefront like this. and a wavefront like this. Okay, so let's just focus on the wavefronts and not on the lines right now. So let's say this is the incident wavefront, again AB. This is C. Now in this case, we'll not take these backward wavelets, we'll take these forward wavelets. So let's say it takes a time t for B to go from B to C. Let's say the speed in medium 1 is V1, the speed in medium 2 is V2, because the difference between two mediums is the speed of light in the two mediums. So this distance is V1t, right? At time t, this just starts becoming a secondary source. After time t, this has already been a source for a total of t seconds. So it will have a maximum wavelet which will have a radius of V2t. Why V2? Because it is traveling in the second medium where the speed of light is V2. So we'll do the exact same thing here. Let's call this D. We need to prove that CD is the wavefront of the refracted ray if AB is the wavefront of the incident ray. Right, now this has been a secondary source for t seconds, so the radius is V2t. This has been a secondary source for 0 seconds, so the radius is 0. All we need to do again is we'll take an arbitrary point, let's say P, such that AP by AC is equal to X, and we'll prove that the secondary source that P becomes at a later time will have a maximum wavelet that touches CD. So for any arbitrary point, we'll be able to prove this, right? So let's take this to be X. Again, so this is X. These two triangles are similar because this is 90 degree, this is 90 degree. These two angles are the same, are common. So these two triangles are similar. Let's call this Q, let's call this R. That means QP by BC is equal to X. That means QP is equal to X V1t. That means the time it takes to go from Q to P is xt. So how much time does it take for P? How much time is P actually a secondary source for? For a time t times 1 minus x. So what is this distance? It is V2t times 1 minus x. Right? Now if this distance is V2t times 1 minus x, this is x, this is 1 minus x. Right? So PC by AC is equal to 1 minus x, and again these two triangles CPR and CAD are similar, so from that we get PR by AD is equal to 1 minus x, which indeed it is. So we see that any arbitrary point, whether it's this point, or this point, it will become a secondary source at a time between 0 and t, and then it will start emitting sources, and they will have a radius of V2 times t times 1 minus x, the remaining time, and we see that any point will have a maximum wavelet which will touch this second line, right, this emergent wavelet. So we proved that if AB is the incident wavefront, the CD is the emergent wavefront. The only thing left to do is find the relationship between the angles. So let's say this angle is I and this angle is R. We can see that sine I is equal to BC by AC. And sine R is equal to AD by AC. That means sine I by sine R is equal to BC by AD, which is equal to V1 by V2. Right? BC is V1t, AD is V2t. So sine I by sine R is equal to V1 by V2. That is also equal to mu2 by mu1 if mu is the refractive index. Right? So we've proved Snell's law, which says that sine mu1 sine I is equal to mu2 sine R. This is how I remember it. Mu sine I is equal to constant. Right? So this is the beauty of the wave construction, based on a simple principle that every time a surface is reached by a wavefront, it becomes a secondary source. We were able to actually prove laws of reflection and refraction and actually derive Snell's law. So we've seen how to derive laws of reflection and refraction using Huygens principle, and in the next video we'll study some phenomena which arise only because of the wave character of light. We'll study YDSE, Young's double slit experiment, and we'll also study the phenomena of interference, diffraction and polarization of light. Thank you.